Hello everyone, welcome to week 1 for Algebra 1B. We're going to dive into a new semester. We're going to be looking at a new topic, systems of linear equations. All right, for week 1, make sure you're reading over the textbook, accessing the textbook, make sure you're taking notes, make sure you're doing all the practice problems and assessments for this week. Use all those little video helps on your paper pencil assignments. And let me know if you have any questions or if there's problems you want to go over. For week 1, here's what we're going to be talking about. If I give you a linear system of equations, we're going to talk about what that is. Can you find the solution graphically? We're going to do lots of graphing this week. Given a linear system of equations, can you tell if a point, x and y value, is a solution? If I give you a linear system of equations, can you solve it algebraically using the substitution method or the addition method? We're going to be introduced to these two methods. And then finally, we're going to look a little bit at word problems with linear systems. So lots of stuff with linear systems of equations. What is that? Linear systems of equations are about working with situations or problems that need to be represented with two or more linear equations. We're still working with lines, still working with equations of lines, slopes, y-intercepts, all of that. But now we just have two at the same time. And for the most part, we're just very interested in where our two lines cross or intersect on the graph. So here we go. Let's start with our first one. Here's a linear system. I've got y equals 3x plus 9, and I got y equals negative x plus 2. I can graph both of these. One has a slope of 3, one has a slope of negative 1. These are not hard, but it's a linear system because both of these are the same problem. They're the same variables. And so we use a little bracket to show that they're the same system. They're modeling the same problem. Let's just dive right into a word problem and use a linear system, go through this whole process all together. Jordan runs at a speed of 8 miles per hour, but he starts a half hour ahead of Haley, who rides her bike at 15 miles per hour. The question is, how long will it take Haley to catch up with Jordan? So we're going to write a linear system that models this situation and start playing around with linear systems and the need for it. So what do we got here? Let's get my pen out. So we've got Jordan. Let's start writing with Jordan. He's running. He's got a rate at 8 miles per hour. So he is going 8 miles per hour. Plus he's already been starting. He started a half hour ahead of Haley. So for half an hour, if he's going 8 miles per hour, he's already gone 4 miles ahead. Okay, now let's switch. Let's take a look at our friend Haley. Haley is going much faster. She's going 15 miles per hour. But she hasn't gone anything yet. So we're wanting to know if Jordan is already 4 miles ahead and still racing at 8 miles per hour, how long will it take Haley to catch up? Well, let's start by making just a chart and kind of visualizing what's going on. Sometimes that helps us get into it. So here we got time. And let's make time go every 30 minutes, right? Well, or half an hour. So we'll go 0 hours, 0.5 hours, 1 hour, 1.5, and 2. Now we've got to keep track of Jordan. How far is he going? And we've got to keep track of Haley. How far is she going? Remember, our goal is to find out, well, when does Haley catch up with Jordan? So there's my chart. We're going to keep track of some stuff going on here. So at time 0, what have we got? So 0 in this case is when Haley starts to run. So when Haley starts riding her bike, Jordan is already 4 miles ahead. 4 miles. And Haley has just started, so she has not gone any distance yet. So she's at 0 miles. Hopefully that makes sense from this problem, right? Jordan's already been going half an hour, and half an hour he's gone 8 miles. So let's go now another half hour. So now Jordan rides another half hour. So now he's gone a total of 1 hour. He's going to be at 8 miles. If he goes 8 miles per hour, he goes 4 miles in a half an hour. So he adds another 4 hours. And we might as well finish it up. If every half hour he's going to go another 4 miles, after 1 hour he's gone for 12 miles. Here he's at 16 miles. And at 2 hours, if Haley's been going for 2 hours, he's now 20 miles ahead. All right, now let's keep track of Haley. She's going faster, so she might catch up pretty quick, right? So if she's going 15 miles per hour in half an hour, she's going to be at 7.5 miles. After 1 hour, she's going to be at 15 miles. She goes 15 miles per hour, right? Whoop, look at that. She's already caught up with Jordan. She's pretty fast. We keep going if we wanted to. After 1.5 hours, she's at 22.5 miles. And after 2 hours, she's going to be exactly 30 miles. So she caught up pretty quick. She might have a much better bike than Jordan, or might just be much stronger than Jordan. But there you go. If I had to estimate it and answer this question using my graph, Haley caught up somewhere between 0.5 and 1 hour. So a little bit after half an hour of riding, she catches up with Jordan. All right. Here is an actual linear system that models that problem. Can you see Jordan going 8 miles per hour, but he's already gone 4 miles? So he's got an equation. His distance, y, equals 8 times x. X in this case is number of hours plus 4. Whereas Haley, she has not gone any distance yet, but she's going at a much faster rate, 15 miles per hour. So this is a system that models this problem over here. Notice we have two equations because we have both Jordan and Haley, but it's part of one problem. How long will it take Haley to catch up with Jordan? Let's take this now and let's graph it and see if that matches up with what we did on our chart. So let's open up the Desmos calculator and graph these two equations. All right, here we are. I'm going to put in y equals 8x plus 4. That's going to be Jordan's. I'm going to put y equals 15x for Haley. And my graph looks a little bit weird, so let's tweak the settings a little bit. So I'm going to not worry about any negative x values. Let's go from 0 to 2 hours, just like we did on our chart. My y values, let's go from 0 to 20 miles, because that was a kind of a good estimate of our chart as well too. All right. So here we can see Jordan starting at 4 miles, that's his y-intercept. Haley starting at 0 miles, that's her y-intercept. But really quickly, Haley starts to catch up in distance with Jordan. And right here, you can see a little bit over half an hour at 0.5714 hours, their distance is the same. This is where she taps him on the back and says, hey, I caught up with you right here. They've both traveled 8.571 miles, and then beyond that point, Haley is much farther in distance than Jordan is. And now we have a graph that shows two linear equations, and the solution, when does Haley catch up with Jordan, is where they intersect. It's where my two lines intersect. Hopefully this is setting the stage for all of this week and what we're going to do with this week, where we need to take problems, figure out two equations, and find this solution point where they intersect. And your graph and your Desmos calculator are going to be huge, huge helpful tools to visualize, see the problem, and check all your algebraic work. Okay, so let's go back and let's start digging into some more deeper topics. We did that word problem with Haley and Jordan. Now we're just going to do some basic skills. Here's a different linear system, y equals 5x minus 9 and x minus 2y equals negative 18. As we work with solutions, as we graph linear systems, sometimes we want to test, is a point actually a solution? So we may graphically find a point, but we want to know, hey, if x is 4 and if y is 11, is that a solution to the system? Well, how do we test solutions? We test solutions by substituting in these values and seeing if it works. So let's start with this first equation right here. Let's put 11 in for y and 4 in for x. Let's see if it's true. So does 11 equal 5 times 4 minus 9? 5 times 4 is 20, and 20 minus 9 is 11. So yes, it's a solution to the first one. But to be a solution to the system, I need to check if it's a solution for both equations. Let's check that one now. So does 4, I'm putting 4 in for x, minus 2 times y, let's put 11 in for y, does that equal negative 18? Well, 4 minus 22, does that equal negative 18? Yes, yes it does. So since it works for both equations, then yes, this is a solution to the system, and we showed it with substituting the x and y values for both equations. So what have we done so far? Linear systems, this whole first week, we've looked at a linear system as just 2 or more equations that model a problem. We did a problem with Haley and Jordan and took the problem and turned it into 2 lines, 2 equations that we then graphed, made a table, and played around with. We can find solutions to linear systems by graphing and finding that intersection point. And then we looked at, we can test a point if it's a solution by substituting the values in for x and y. Kind of setting the stage for what we're doing, linear systems. Now let's get into some nitty-gritty. We can graph them on our Desmos calculator. We can look at where they intersect, but sometimes graphs can be misleading. We may not get exact values. Remember when we did Haley and Jordan, we had the x value was 0.571 and the y value was like 0.8 something. Those are rounded, so sometimes we want to find exact values, or sometimes our values we're working with don't make sense to graph. We're dealing with large numbers. So there's a couple ways where we can algebraically find the solution to a system, but then we'll still graph it to check our work. So the first one we're going to learn for algebraically finding a solution is called the substitution method. What do we mean by substitution? Well, we already kind of do substitution. Take this problem right here. Here's a linear equation, right? Y equals 2/3 times whatever x is minus 5. If I tell you, hey, x equals 12, can you find y? You could all do that. You would substitute 12 in place of x because we just said x equals 12. They're equal, so I can shift 1 around and we get y is equal to 2/3 times 12 because x is 12. We can substitute in place of that, minus 5. And if I calculate that out, I see that 2/3 times 12 is 8. 8 minus 5 is 3. Piece of cake, right? Substitution method for solving a linear system is similar. I substitute something in place of something else because it's equal. There's a lot of steps, so don't let this overwhelm you. But basically, we take one variable, get it isolated, and we're going to substitute one equation into the other. So let's start with that. Start with number 1. Here's my linear system over here. I've got y equals 5x minus 9. I got x minus 2y equals negative 18. The first step right here is in one of the equations, I need one variable isolated. That means either y is all by itself or x is all by itself equal to something else, or whatever variables I have. In this case, I've got y isolated right there, and it's equal to 5x minus 9. So step 1, I'm feeling good. I've already got an equation with one variable isolated. Step 2 now says substitute the equation into the other. This is why it's isolated. So my y variable is equal to, it's the same as 5x minus 9. So in my other equation, when I see this y value right here, I'm going to substitute everything that y equals into to that y right there. So y is equal to 5x minus 9. I'm going to put 5x minus 9 in place of the other equation right there. So here's what we got. We have x minus 2 times y, but I'm substituting something in place of y, equals negative 18. So there's my original equation. I left a big blank where y is because now I'm substituting everything y equals. Y is equal to 5x minus 9. So if I put 5x minus 9 right there, that's the same equation. It used to be y, but I substituted 5x minus 9 in place of it. I now have one equation. Well, we did substituting. I now have one equation. The only variable I have is x. And I can now solve this for x. I like that. I like being able to solve stuff. All right, so let's draw my line. Let's solve for what x is. Looks like I need to distribute a negative 2. So we've got now x minus 10 times x plus 18 equals negative 18. So we distribute the negative 2. Let's combine like terms. X minus 10x is negative 9x. I'm going to subtract 18 from both sides. So negative 9x equals negative 36. Divide both sides by negative 9. And x equals 4. All right. So we solved this resulting equation for one of the variables. We just did that. We got x equals 4. What does that mean? It means if I graph these two lines, where do they intersect? They intersect at an x value of 4. But I'm not done because I don't know the y value. I need to solve for both x and y. Two variables, need to find both of them. So here's where we do step 4. I need to back substitute. Now that I know what x is, substitute that in to find the other variable, to find y. All right, so let's take the first equation. Y is equal to 5 times whatever x is, but now I know x is 4, so let's do 5 times 4 minus 9. So y is equal to 20 minus 9, and y is equal to 11. All right, if x is 4, y is 11. That might be my intersection point. But it's always good to check your work. We like checking your work in algebra. So take this other equation. Let's put x and y in and see if it works. So does 4 minus 2 times 11 actually equal negative 18? Yep, 4 minus 22 equals negative 18. That checks. And then I could also check by graphing. If I found this is the solution and I graph it and it also shows that's the solution, that's a pretty good way to check your work. Solve it algebraically, graph it, and just make sure your answers match. But there you go, that's the substitution method. Make sure you practice that a lot. You want to get to where you can kind of go through it efficiently and get comfortable with all the steps and how to find your solution. You're also going to be introduced to the addition method. It's another way of taking your two lines, your two equations, and combining them in a way, but instead of substituting, you're going to add them together, but you're going to add them in a way where you still end up with a new equation that only has one variable that you can solve. Now here's the easy way to set this up. So take a look at this. This is already set up to see. But what happens if I add these two equations together? Well, we can only add like terms, so it's helpful to line up your x values, it's helpful to line up your y values, and it's helpful to line up your constants. So when I add things to both sides, I have 3x plus negative 3x turns into 0x. 3 plus negative 3 is 0, right? 5y plus negative 4y is going to become just 1y, positive 1y. That's equal to 18 plus 10 is 28. And look at what we have. If I take away the 0, I just see y is equal to 28. We just found half of the solution. If I graph these two, apparently they're going to intersect at a y value of 28. Well, to find the other value, we just substitute it in. So let's put 28 in for y and solve for x. So does 3x plus 5 times 28 equal 18? I'm going to solve this equation for x. 5 times 28, that's going to be 140. So 3x plus 140 equals 18. Let's subtract 140 from both sides. Let's solve this equation. 3 times x equals negative 122. And if I divide both sides by 3, we get x equals, 3 goes in on negative 122 40 times, negative 40 with the remainder of 2/3. So guess what my solution is? At negative 40 and 2/3, there's my x value and a y value of 28. That's where my two lines will intersect. That's the addition method. It's adding them in a way so that either your x value goes to 0 or your y value goes to 0. In this one, the x value turned into 0 all by itself. Now we can check our work by graphing, so let's just do that. We got a kind of a weird solution. Maybe I don't believe it. Let's actually graph these two and make sure it works as well. So I'm going to open up my Desmos calculator and graph this. Okay, here is my two linear equations. I've graphed them. Now, just on the looking at our default window, they don't look like they intersect, right? Sometimes you have to zoom in or zoom out. And now you can kind of see, oh, it looks like they're going to start narrowing to the left here. And we can move things around, pan our graph over, and there is the intersection point. Now remember, we found a y value of 28. Well, that matches up with the graph. And we found an x value of negative 40 and 2/3. Well, it's the same as negative 40.667. It's not exact because our graphing calculator can't give us exact fractions. So it's giving us the decimal approximation. But this definitely is showing that what we found algebraically using the addition method, it is right on. It is the intersection point, the solution to where these two lines intersect. Let's take a look at one more. So in the addition method, remember our goal is to add them together so that one of the variables turns to 0. Sometimes we have to do a little bit of work to get that. For example, what happens when I add these two together right now? 2x plus 3x gives me 5x. 5y plus negative 4y gives me 1y. 9 plus 22 gives me 31. And I do get a new equation, but it's still got x, it still has y. I can't solve that. That's not helpful for me. So I need to do some work ahead of time so that when I do add them together, I want a 0 for my variable. For one, the x, or I want a 0 for y. So let's think about what we can do here. I'm going to rearrange this. I've got 2x on the top and 3x on the bottom. What happens if I multiply the top by negative 3 on both sides? I'm going to multiply each term by negative 3. And I multiply the bottom by positive 2. So I'm multiplying both equations. Negative 3 times 2x is going to give me negative 6x plus negative 3 times 5 is going to be negative 15y equals negative 3 times 9 is negative 27. So multiplied both sides of the top equation by negative 3. Now I'm going to multiply both sides of the bottom equation by 2. So 2 times 3x gives me 6x plus 2 times negative 4 gives me negative 8y equals 2 times 22 is 44. Well, now what happens when I add these together? Negative 6x plus 6x, 0x. Boom, I like that. This means I can get somewhere now with the addition method. So let's do the rest of this. Negative 15y plus negative 8y is negative 23y. I can ignore the x term because that went to 0, equals negative 27 plus 44. That's going to be, oh, this is like blowing my mind for a little bit. Okay, 27, 44 minus 20 is going to be 24. 24 minus 7 is going to be 17. Well, now it's just one more step. Divide both sides by negative 23, and we know what y is. Y is equal to negative 17/23. Now that is an ugly, ugly, ugly fraction, but we were able to solve it. We got that ugly fraction solution, and it didn't really take that much work at all. So now we know that these two lines are going to intersect at a y value of negative 17/23, and that's exact. But what if I want to find now the x value? I could substitute negative 17/23 in for y and start doing some stuff, but that's not fun. I don't want to do fractions. So let's do another addition method, but this time, instead of getting the x's to turn to 0, let's get the y's to turn to 0. So to do that, I got 5y, I got a negative 4y. I'm going to multiply the top by 4 and the bottom by 5, just like we did with negative 3 and 2. So here's my new system. I multiply the top by 4. I've now got 8x plus 20y equals 36. I took the equation, multiplied everything on both sides by 4. And on the bottom, I'm going to multiply by negative 5. So now on the bottom, I've got negative 15x plus, whoops, I don't want negative 5, I want positive 5. I already got a negative 4, so I want positive 15x plus negative 20y. Remember, I want positive and negative. I want these to add to 0. Equals 110. 5 times 22. Now what happens when I add these together? My y's go to 0. Yes, that's amazing. So now let's just deal with the x's. 8x plus 15x is 23x equals 146. So if I divide both sides by 23, let's find out what x equals. X equals 146 divided by 23. That's again an ugly fraction. How many times does 23 go on 146? Let's see. 23 times 4, 23 times 5, 23 times 6. Goes in 6 times, so x equals 6. And 138 times 6 times 23 is 138, so that leaves a remainder of 8. 6 and 8/23. So, ugly solution, right? But they intersect at an x value of 6 and 8/23 and a y value of negative 17/23. We may feel like we did some mistakes, but let's check it graphically. So let's graph these and see what we got on our decimal calculator. All right, here we are at our graph. I've got 2x plus 5y equals 9, 3x minus 4y equals negative 22. We found using the addition method that they intersected at an x value of 6 and 8/23 and a y value of negative 17/23. But let's look at our graph. So where my two lines intersect is right here. And look at that. There's 6.348. And I bet you if I take 8 divided by 23, that's going to be about 0.348, right? So I'm feeling good about that. And negative 17/23, if I turn it into decimal, it's, there you go, negative 0.739. My graph is definitely confirming all the algebra work that I did. So I'm feeling 100% on my job. I like that. I just checked my work. Well, there we are. Week 1. Welcome to semester B. We're diving right on in. Good work today. We did a lot with systems of equations. We did graphically finding solutions, took a word problem and kind of broke it down with a chart, made an equation and represented that solution where they intersect. And then we really did some hard algebra work, learning about the substitution method and the addition method as ways to solve linear systems. So make sure you're reviewing this, get some good work done for week 1. so that you're ready as we do more with linear systems next week, that you're understanding and comprehending everything as well. You can use your Desmos calculator a lot to check your work, visualize, make sure you're understanding what's going on. Let me know if you have any questions.